All right, for part A, if you can just look at it and know what to do with it, then great. I'll go ahead and show kind of the if in doubt expanded out version. So plugging 0 in for n would give us 1, plugging 1 in for n gives us 1, and so on. Okay, so for this one, you could have two arguments. So you could say that it is geometric with a common ratio that is equal to 1, and therefore it diverges. And not only does it diverge, but when you expand it out, you can tell it diverges to infinity. There we go. That's one explanation that you could give for part A. You could also use the nth term test for divergence argument. Since the terms themselves at the tail end are not 0, they're 1, then you could tell for sure it's going to diverge. And so you could also say that it diverges, and then specifically to infinity. Now, it's the fact that it diverges to infinity, I could tell that because I expanded the terms, but it diverges by the nth term test. Okay, and never just stop after saying test there. Always say for divergence. There we go. So either of those explanations would do it. Okay. For part B, let's see, if in doubt, expand it out, right? So starting with n equaling 0, we'd have 3 to the 0, which is 1 over 7 squared. Plugging 1 in and plugging 2 in. There we go. It looks like it's geometric. What is its common ratio? Looks like they're multiplying by 3/7 every time. And so, oops, r equals, or there we go. And then we would know, therefore, it converges. What does it converge to? It would converge to the first term, which is 1 over 7 squared, divided by 1 minus the common ratio, which is 3/7, which would equal 1 over 7 squared times, let's see, 1 minus 3/7 is 4/7, so 7/4. So the answer would be that the sum would end up equaling 1 over 28. There we go. Okay. Let's see, part C is equal to 0.1 plus 0.1 plus, whoops, I should do 3 terms or more, I suppose. There we go. And so what do you think this one does? I would definitely say it diverges to infinity because you have infinitely many numbers that are, not approaching 0. Anyway, so this one you could actually use the geometric argument if you want. The common ratio would be 1. And so you could say it diverges, but I personally would use the nth term test. So I would say it diverges. I can tell it diverges to infinity just because I expanded it out. But it diverges by the nth term test for divergence. Always make yourself write that for divergence part. You'll be so glad at the end. Okay, let's see, part D here. If you start expanding it out, you get negative 0.5 plus 0.5, negative 0.5, that is. Negative 0.5 squared plus negative 0.5 cubed, like so. Up to you if you wanted to expand it, but I would definitely say that the terms you can see do go to 0. That doesn't mean that it converges. It just means that it, you don't know for sure that it diverges. It could go either way. But this one also is geometric. So I'm going to use the geometric argument here, and that would be the only argument that would be acceptable on this one. So this one is geometric. The common ratio is negative 0.5, which is between negative 1 and 1. And so therefore, it converges. And what does it add up to? The first term is negative 0.5 divided by 1 minus, and the common ratio is negative 0.5 as well. All right. For some reason, I prefer fractions for this. So you'd have -1/2 over 1.5 or 3/2. Flip and multiply. The 2's cancel, and you'd be left with -1/3. There we go. All right, my friends. So parts A through D, we're focusing on just practicing using, geometric series and the nth term test for divergence. Same directions for parts D and E. Determine if it converges, and if it does, evaluate it.